Okay, and we have a long, roughly 10 years collaboration with Simon Lin and his group under the DMCC disaster mitigation. So I'm very happy to share some experience on this experience. So this is me, and currently I'm working at National Central University, and I just stepped down from the Director of Hydrological and Oceanic Sciences. And if you want to contact me, you can use email or use Facebook. Okay, I will start from very convention tsunami introduction. That is the 2004 Indian Ocean tsunami and an earthquake. All right. So it happened in 2004. And here I don't want to emphasize the detail, just give you some thought that after this event, what did we learn from it? So the event happened here, and the earthquake magnitude was very huge. It reached to 9.3, ranked as second one in the history, in the human history. And the rupture length is roughly 1,500 kilometers long. That is extremely long. So by the time we have the animation for that, and you can see the resolution is very poor, right? And by the time we were very happy to see this result, all right? And also we have the arrival time for that, but this was for NOAA because Simon and Eric told me I have to change my result, the details. So I just grabbed some results from NOAA, but very similar. All right. And this event caused a very large number of deaths toll, 290,000 people or more dead. And I visited there. That one thing impressed me was the wave height. The wave height, here you can see this 3-floor building, and each floor actually is roughly this high. So 3 floors is roughly 10 meters tall, and you can see the roof is swept away by the tsunami wave. And I often being asked how to survive in tsunami, and my answer is only one: don't get wet. I don't know how to answer the question, because if you are facing this kind of huge flood, how can you survive? I don't know. So try to keep dry. That's all. How to keep dry? Climb higher. Right. So from this event, a lot of scientists or researchers thought they learned a lot from this event, and also from the Chile earthquake. That is, the giant earthquake usually often occurred, and not often, by the time they say always occurred, on a very long and straight change. Okay, and unfortunately, when people thought they are very understand the earthquake and the tsunami, then 2011, another tsunami happened. That is the Tohoku earthquake and the tsunami. As you can see, the tectonic plate actually is not a very large plate. I say locally. This happened here. Actually, is the interaction between 1, 2, 3, 4 plates. Usually, before this event, 2011 Tohoku earthquake event, people thought here the largest earthquake might exceed magnitude 7.8 or 8.0. But unfortunately, this time the earthquake magnitude was 9.1, and the length, the rupture length is relatively short, only have 500 kilometers. So that gives us a lot of So in the academic area, we actually start thinking maybe we have to, facing the nature hazard, we have to raise the safety level, because if we don't know what really gonna happen. So lessons learned from the 2011 Tohoku earthquake. One is the devastating earthquake will occur on a long and straight change. No, I just say it might not. And the other questions like the tsunami disaster can be prevented by coastal vegetation. We don't know, maybe yes or maybe not. Or the RC building, reinforced concrete building can against the tsunami wave. Well, we don't know. Usually people think yes. And the tsunami wall can against the tsunami, can really against the tsunami, because people think when the tsunami comes, we can just build a wall to against that. And also, the tsunami early warning can rely on the coastal buoy. And the last question, sorry, I didn't transfer this one into English. The last one is the tsunami early warning, because often people just calculate to the shoreline area. They didn't do the inundation, because if you want to simulate the tsunami inundation, that requires much more time and higher computer technique. So people usually think, we can calculate arrival time to the coastline, that is enough. So I put a lot of question mark here, and I'm going to give you some examples for those questions. The first one is the pine tree, or as we say, the coastal vegetation distribute along the beach. This is located at Rikuzen Takatachi. Sorry, I'm not very good at this. All right. Takata. Okay. This is a beautiful trees here, and unfortunately, the tree is actually destroyed by the huge tsunami, and only one pine tree left. And this pine tree was called Pine Tree of Hope. Just like previously, I showed you the boat. There's only the boat on the roof. There's hope, hope of the boat. Okay. The thing is that the pine tree actually not only destroyed by the tsunami, it became debris, and the debris can make more extra damage to the disaster. So to answer the question if the coastal vegetation can really protect people, the answer is yes or not. If the wave height is not over the tree, usually yes, the tree can survive. But if the wave height higher than the tree, then the tree can bring the momentum and hit the building and the people and cause severe damage. Okay, so this is the first question. The second question: the RC building can survive in the tsunami event. Unfortunately, here shows a lot of examples that the building was destroyed. This building was not pushed over by the tsunami, but it's broke directly and turned over in the tsunami wave. So the tsunami wave force reached to about 50 tons per square meter. So if you want to say if the building can against tsunami, the answer is still yes and not. Because if the building consider the wave force, then the answer will be yes. But if not, then the answer is not. The other slide will show you some buildings in the tsunami. Okay, so this is the building in which city? Let me see. Oh yes, thank you. There were two buildings. One is the city hall. The other is city office. Okay, the city hall was beautiful and totally destroyed by the tsunami. The other one is city office. Okay, this is the city office after the tsunami. It looks okay because it kept the shape. But if you look at the details, you can see that debris actually penetrate the buildings. So even though the building survived, but the people cannot survive in the building. Okay, so the next example is the seawall. Okay, the seawall sometimes called the Great Wall by the local residents. Okay. In Japan, they have the very huge and beautiful seawall. The seawall was so huge. This is the regular seawall. This is the Great Wall. Okay, and unfortunately, the seawall still cannot survive in the tsunami attack. So does that mean the tsunami, even though the biggest seawall cannot against the tsunami? The answer is still yes and or not. This is the other side of the seawall. The seawall only have a small section left survive in the event. But even though that survived, the other side of the building was destroyed. Here shows another strange example. This is the seawall built by a village, chief of the village, 30 years ago. The seawall, you can see that is much thinner than the previous one, but much taller. This seawall was 15 meters tall. And the village chief actually was argued by the people in the village because they think that the seawall was too expensive. And it's not necessary to build a seawall that tall because the other one is just 10 meters tall. This one is 15 meters tall. But in that, the chief insists to build this 15-meter seawall because he say in the history, 1896, the tsunami high was 15 meters. So if the seawall was not tall enough, high enough, then it's useless. So this is the only one seawall that survived in the event. So if the seawall can against the tsunami, the answer is still yes and or not. If the seawall is tall enough, yes. It's not. If not, then not. Even though it's huge, but still. So that tells us that to estimate the tsunami height is extremely important for the hazard mitigation. Okay, so this shows the results, totally different results. Huge, but not tall. Thin, but tall enough. So that tells you that grow your children taller. That will help you a lot. Okay. Just joking. Okay. So another thing is the tragedy of Okawa Elementary School. So this event was famous because there were 70 students died and 9 teachers lost their life in this event. This location is here. Okay. Actually, here is the ocean and the big river, and they're located here. Okawa, the name was big, so they treat the big river as the mother. And unfortunately, in this event, the tsunami actually flooded along the river. The event make people think again was because actually in this event, the teachers have more than 15 minutes to escape the students. When the earthquake happened, the based on their SOP, the teacher lead the student to escape to the ground. This is correct. But after that, there was some information about the tsunami will come, but like the teachers really they probably don't believe that, because in the past, in the history, they never have a tsunami really reached to that deep. Okay. So they still leave the students on the ground and waiting for another information. So before 7 minutes before the tsunami came, finally the teacher think the tsunami is really coming. So they lead the students. Here's the school to the bridge, the suspension bridge. It's very normal, because the school actually is high ground, and the land was used as a escape area, and not to say this suspension bridge. So people think suspension bridge is might be tall enough, so and very close, so they just lead the students run to the bridge. But unfortunately, before they reach the bridge, the tsunami came, so most of the students died. Some of the students really reached the bridge. This is the bridge. Unfortunately, the bridge was blocked by the tsunami. So even though they can reach to that point, they still cannot survive. Only a few students and the teachers reached to the mountain side. Sorry. Here is the mountains here, and they survived. So after this event, lots of parents argued that how come the teacher won't let the student go to the mountain, because they have field trip to the mountain before. And the survived teacher said because they are afraid of landslide and the tree falls. This is very reasonable, all right? So this event actually tells us that if you do the hazard mitigation without really consider the inundation, you might give people two mistakes. First, the regular people, normal people it's very difficult to estimate the tsunami arrival time, not close to their house. It's very difficult to estimate the time lag from the coast to their buildings. In this case, they don't know what's the time lag. Secondly, they don't know which area is safe. They based on their experience, lead the students to stay here and then run to the building. Two mistakes. Both are wrong. Okay. If they have a very detailed simulation or scenario study for the inland area, they might know here is the only safe area, safety area. Okay, so this is the one tragedy that actually help people to really think again about the tsunami hazard mitigation. So and let's go back to what I did in Taiwan. So in Taiwan, our government and our people often ask, will Taiwan be attacked by tsunami? So so I try to answer the question from four aspects. One is the distribution of the change nearby. Second is the historical record. The third one is some sediment deposit and tsunami borders. The last one is my scenario study. So this is the change distribution obtained from USGS. Here you can see on the east side of Taiwan is the large plate. It's called Philippine plate, C plate, Philippine C plate. And here have a lot of changes, and colored in red means hazard appraisal is high. As you can see, this issued in 2006. I remember 2006, before the 2011 Tohoku earthquake. You can see Tohoku earthquake actually already colored in red. And the other colored in red is the this one, Nankai Trough. The third colored in red is the Manila change. So that's things we missed one. We should have missed the second one and then the third one. So then our most it's similar to the NSF in USA. Asked me to do the study to figure out how many what's gonna affect what kind of tsunami will affect Taiwan. So I organized a lot of meetings to collect people from geoscience, from earthquake, and to make this map. So this map tells us that the largest possible earthquake might happen along the change. So you can see here, Manila change is short. We separate this one into 1 segment, 2 segments, 3, 4 segments. So the earthquake, the largest potential earthquake will relate here to the length of the segment. So this one is short, so we say it's 8.2. But maybe the next version we will link these two together because we don't know if the earthquake can really stop at this point from here to here. But anyhow, this is the first version. So 8.2, 8.4, 8.6, 8.0, and so on and so forth. So before I show you the result, I'm going to show some model that speed up by Dr. Lin's group, speed up a lot. This model is called COMCOT. COMCOT model is a corneal multi-grid coupled tsunami model. It was very famous in the academic area. So people use this model to do the research. And this model has a lot of capabilities. First, because the multi-grid, so you can use a very coarse grid up to connect to a very small grid, link them together, and two-way coupled. So that means that we can do the tsunami simulation for a very huge area and up to very small scale. So it can cover the whole tsunami life. And then this model can solve the linear and the nonlinear shallow water equation on both or either spherical or Cartesian coordinate. It's a very strange model that can do this kind of strange thing, but it's very useful because if the scale is large, then spherical coordinate should be the only choice. And use the multi-grid, and it can do the moving boundary. Moving boundary is very important because that means that I can calculate the inundation from the wet area to the dry area. Okay, so it was very good in research. Why I emphasize in research because it usually takes 3 to 6 hours to finish one case. So when we finish the case, the tsunami event finished. So it's useless. No, I mean, useless to hazard mitigation. So fortunately, EMCC group helped me to parallelize this code and make this code very fast. And this one is also being widely validated. I just show you one example. This is a very famous example. It's solitary wave run up and run down. So this is the comparison between, this is the slope and the wave coming in and run up and going back. And the dot lines are the laboratory results. Solid line is the numerical simulation. So there are a lot of functions in this model, and the most important issue is the model was developed by my advisor, so I have no choice. You know, right? Okay.
OK 了，看到没有
So this is very fast and
太夸张了！哇，听到声音了，哇，太过瘾了！这是我们以前的效能。
the cluster that makes people happy, make the nerve.
我那电脑是噔。
Yeah, you can see the fan. Okay. So when we finish this model, then we have a chance to practice this case. Then 2011 Tohoku earthquake happened. So we spent about 20 minutes to wait for NOAA and USGS to report the earthquake parameters, the detailed parameters. After that, when we received the data, Compa only spent 1 minute to finish the tsunami simulation from Japan to Taiwan. So it's even beyond the real-time simulation. So by the time our hazard mitigation institute under the government is called NCDR. They called me, asked me what's gonna happen because you can see the news report saying the people in Taiwan, some female students were crying because they think that this is their last day in their life. So people in Taiwan were nervous. Then they asked me, what will the wave height be? And I say 12. Okay. I still remember this joke. And then the NCDL, the people on the other side, I can hear that 12. And they're very nervous because they have to organize and ask the president to join their meeting. I say 12 centimeters. And you can hear the other side of the phone. And they say, okay. Then after that, the weight gauge data shows 12 centimeters. So this is the first version simulation results. Okay, it's by Comcast. So the wave will actually behaves like an edge wave coming along the neutral change and to Taiwan. And the wave was very small. But most of people don't understand tsunami by that time. They think Japan and Taiwan was very close. And the tsunami in Japan so scary, they will cause damage in Taiwan. So, okay, so then I compare the results with some gauge. One is the gauge in Japan, and here is time history wave height. One is the observation, the other one is the simulation result. I have to say this is very accurate because if you know, then the tsunami wave height prediction smaller than 100% is called accurate. This one is very, very accurate. The other one is from USA NDBC and still amazingly good. Yeah, even better. And ironically, on the other side of Japan, in Russia, they received some signals, very, very small, only 10 centimeters. But we can also capture the wave height. So very good. But most importantly, can we really have a good result in Taiwan? Because the wave have to pass a lot of small island along the Ryukyu shore. But you can see the result comparison is very, very, very good. Right. So our government asked me to do the study to figure out was there really some damage in Taiwan. Then I do the simulation. So this one is very important, I think. This is called the nested grid I use by that event. I use 6 layers. Actually, never have any people use 6 layers. The 6 layer from about 3.5 kilometers up to 2 meters. Okay, and I overlap a lot. So along Taiwan, we have 2 meters. Some places, for example, close to the nuclear power plant, the resolution even up to 1 meter, and including the inundation. So people can really know what happened when the wave flood to the inland area. And but if you want to do, if you were doing the tsunami simulation, you might know that in the public domain, the best resolution you can get probably is 500 meters. Then how to obtain the 2 meters resolution? This is the secret of classify the data. So in this event, in this case, is our national president asks the military to provide me the data. Okay. So sometimes we need some opportunities that can get the result. So as you can see, the source of the bathymetry included the eTopo, GAPCO, and from Navy, and from NCU is my university, and from the satellite, and DEM, and also Thai Power Company. Our Thai Power Company asked people to ride the boat to use the stick to measure the water depths. And resolution can reach to 1 meter. Very cool. So this is some scenario for the initial wave height. We even consider the asperity. Asperity means that the initial wave is not uniform in this direction. You can see here is higher, here is higher, because as in the Tohoku earthquake, you can see that the rupture dislocation is not uniformly distributed. Some places is much higher than other places. So we have some paper published to discuss this percentage. So this is the result. Sorry, I missed the first scenario. The first scenario was here. This is the second scenario. The second scenario shows that this is the north part of Manila Trench, and the wave will attack Hong Kong and Macau, and also Taiwan, and also here they have in mainland China there's a nuclear power plant. The number 3 will attack Hong Kong and Macau, and the next one will attack mainly Hong Kong, Macau, and also Vietnam, and not to say the Philippines, yeah, definitely. And here's Manila city, and here we'll transfer the energy to Japan. So you can see if the coastline is colored in red, then that will be dangerous. So the other one is still very strange. Japan is on, but Taiwan looks like off. So the Yap change, the number 8, will project the energy to Taiwan directly. So in Taiwan, we will very care about this event. Number 9, Mariana change, and the first change just beside the Yap change, but the energy will totally goes to Japan. And the number 2, the number 10 still to Japan, and number 11 to Philippines and also Japan. It's very odd.
You did Hawaii also?
Oh no, I didn't. I didn't.
One is usually covered.
Guam is covered. And here is Japan. And the next Japan. So that's why Japan is the home of the tsunami. And it's definitely the tsunami should be named by Japanese language. Because from the 18th scenarios, only 3 to 4 will attack Taiwan. Others, almost all the events will go to Japan. Like I like to travel to Japan. So in Taiwan, I tell our government that we have to very careful about some scenarios. So one scenario is underneath Taiwan, that's Manila Trench. And from the GR law, it's very famous relationship between the earthquake magnitude and the return period. So GR law shows a straight line that helps us to predict a larger tsunami, the return period of larger earthquake. So here shows the earthquake from 8.5, the return period is about 200 years, and the 9.0 is about 700 years. So it's a very regular return period. And also from the GPS measurement, it shows that the tectonic plates against each other, the largest displacement is around here. So this also shows if here something happened that will attack Taiwan. So then we published a paper that saying if we consider all the events along the Manila Trench, then what's going to happen? So it shows the energy distribution in this map. So this map shows that most of the energy actually coming from the largest dislocation will reach to Hong Kong, Macau, and Taiwan.
T2 and T3
Like that's right. T2, T3, T4, and T5. Actually, T2 will go to here and here. T3 will go to here, and T4 will not transfer to here. So it's directly to Vietnam, and the T5 is to Manila City. So then this paper makes people in Hong Kong nervous. So lots of news interviews from Hong Kong. So this is the animation for T2. So then I zoom in Taiwan, because Taiwan is very small here. And you can notice that some places were colored in red. So on the end of here, make our government very nervous because we have nuclear power plant number 3 located here. Not to say here's a famous tourist spot. It's called South Bay, a very beautiful beach here. So our government was very serious about this result. So they asked the Thai power company to have some strategies for tsunami event. And also the government have the first nationwide tsunami drill in Taiwan. And this is my name, and here is some directors in different departments in the government. And as I usually say, this seat, usually this is drill. If this is not drill, this seat is for the national president. So they treat this seriously, but the result seriously. And the Thai power company now is building seawall to prevent the tsunami event.
But the previous one shows that the one before, just to, yeah. No, this then before the one before. The height here was at least 10 meters.
18.
No. Okay.
It's over. Yeah.
The South Bay is 18 meters. 18,
and here is 12, and here is the coastline, and here you can see the inundation.
Oh, the coastal is here.
Yeah. So the wave will flood to the very dangerous. Yes.
So what is the height of the nuclear power plant here?
12.
No, the wall.
Actually, the ground is 12.
Yeah. Okay.
So but based on the law for the nuclear power plant, they have to consider the buffer zone.
Yeah.
So they build, even 12, they build 6 meters tall. Yeah. Because just as I said, no people can really 100% say the tsunami is 12, then 12. Then this afternoon, this evening, my students gonna show something about the model. And DMCC and under the lead of Dr. Lin, they even create the cloud-based tsunami system. Is called IconCAD. All right. So you can use that one on iPhone and iMac, iBook.
I watch now.
Okay, I watch.
No.
All right. So it was interviewed by UK and also have invited speech from UNESCO. Actually, last year we also have a talk in Xiamen for UNESCO. And National Geographic has a report on this. And MOST, which is NSF, similar to the NSF in the USA, have a column for that. Then we built a tsunami fast calculation system for our Central Weather Bureau. This system is very important because when the earthquake happened, usually people can get the very early information in 1 minute. The information include longitude, latitude, which is the location of the earthquake, and also the focal depth, and also the earthquake magnitude. Okay, but if we want to do a really tsunami simulation, we need much more than this information. We need actually include the strike deep slip angles, and also the rupture length and width, and also dislocation. So this is for people will get the information in maybe 1 to 1.5 minutes, and to here maybe 20 to 30 minutes. So, but tsunami is dangerous, and we need time. So we build a fast calculation by sorry. How to do that? We have another paper published that is based on some statistical and geological study. When we get the information for longitude, latitude, and the focal depth and the magnitude, then we can automatically create all the parameters. Okay, so we can create the initial wave height, wave profile. So and do the simulation. And if we getting more information, then we can rerun the simulation, because all the simulation can be finished from Japan to Taiwan is 1 minute resolution up to 500 kilometers. And if you want to do a large domain simulation, for example, from Chile to Taiwan, it takes about 30 minutes. But it's still faster than tsunami coming to Taiwan, because from Chile to Taiwan, it takes about half day to 1 day, much longer time.
Because, yeah, tsunami travel the speed of airplane.
That's right. Yes. So then we try to validate our model. So as you can see, we pretend we don't know the detailed information for 2011 Tohoku earthquake, and use our model to do the early calculation, and also use the complete parameter to do the complete simulation. So this column is the parameter guessing from our model. This column is the complete parameters from GCMT. And here shows the result, like the one buoy in Japan, in Russia, in USA. Ironically, it seems that the parameter guessing from our model is more accurate than GCMT. Okay, that I don't know why, but anyhow, it's an encouragement.
So this is more accurate than that one?
That's right. Yes, it's up to here. Yeah. But similar, I have to say similar. Okay.
You know, that means the extractive and the parameter are accurate.
So I would say this may be case by case. This case we were lucky. Maybe the other case, that one will be better. But anyhow, I think that can help people. But there's another problem that when the earthquake happened, earthquake have at least three type of earthquake. One is the against to each other. The other is to leave each other. The other is horizontally. If the earthquake happens for this kind of movement, then no tsunami because there's no vertical disturbance. But in our scenario, we always use the worst case scenario to do the simulation. So it might give people false alarm. So this case is okay because this is the typical against the kind of subsidence. But the most of the cases might not that lucky. So later I will show you some how did we overcome this problem. But before I reach to that, I'm going to show you some benefits of using ComCAT. As you know, tsunami came maybe 200 years once. That means we can only get funding 200 years once. But if you consider the typhoon or hurricane, they came to visit Taiwan 4 to 5 times per year. Okay, it's 1,000 times in terms of frequency, higher than tsunami. So then we try to transfer tsunami into stone surge. All right, actually very successful because they all solve the shallow water equation, and the stone surge model usually cannot do the spherical coordinate large scale, but we can do that. This is our fundamental, right? So we add the wind stress and the pressure force and the radiation stress into the model, make the ComCAT become the stone surge model. And also we coupled with TPSO tight model. They're all done by my students, Mr. Lin. Okay, Mr. Chai, sorry. Mr. Chai. Maybe I have another one. And the tight comparison is very, very satisfactory because you see you cannot tell the difference. So this is the coupling with the Wolf model, very, very good. And last year, our model become the official stone surge model, which provide early warning for our government. So in the official website, our Central Weather Bureau will show you this green line is the prediction from the stone surge model, and the dotted line is the measurement from the buoy data, from the gauge data. So this comparison make us very nervous because you can watch this one, and if the dot away from the green line, that make everybody nervous. All right, but anyhow, you can see the result looks pretty good, pretty good. So now if you go to the official website in Taiwan, earthquake and the stone surge are all reported by us. Right. Okay, so this is a very short commercial time. So we have the fast calculation system that can provide early warning. And the next one is the historical record. So in Taiwan, actually, Taiwan is much smaller than Japan. The areas are 11:1 to the Japan is the area. And the coastline is also much shorter. And not to say the area and the coastline is shorter. The history is also shorter. The history in Taiwan is only 350 years, starting from 1661, Koxinga overtake Tainan. So only less than 400 years, we actually have a lot of tsunami events. So I try to tell people in Taiwan that Taiwan is not a tsunami-free island. Based on the scenario study, shows at least 3 different scenarios will affect Taiwan. From the historical event, there are a lot of events will affect Taiwan. All right. So here shows here have some events I just show you briefly. And also, I sent the students, including Mr. Tsai, to that the coast area, and they didn't see the historical record, nothing. But they found another record that is here. Here is around this area. They have 4 temples saying the tsunami event. There are 4 temples. They said the temples, one is in their dialogue. They said because tsunami came, so they have to move their temple to the inland area because the original area was under the water. Okay. The second one puts the history here on the wall, saying the same thing. The third one on the ceiling. So this is the on the ceiling. They say the same thing. The last one, they even explain why it happened. They say the Dutch people came to Taiwan and cut the tree and make the feng shui change. So, okay. So 4 different temples saying the same thing. That means the event is very possible. And also we found the tsunami borders in Taiwan, 2 of them. So overall, we have a tsunami event, so many events in very short history. So, but I'm thinking, okay, now I can do the best calculation, but I have to wait for the event. And I can do the scenario study, but does that mean I have to do scenario by scenario, do a lot? So I asked myself, or somebody also asked me, before the event, can I know where is the dangerous location of the tsunami source? And also, is that possible not using a computer? You know, when people are panicked and the earthquake destroy the power system. Can you really get the information? So here, I'm going to briefly show you a brand new method for tsunami hazard mitigation. I use 2 different methods. One is called IIA. The other one is called STR. IIA is impact intensity analysis. The STR is seismic tsunami relationship. This idea actually coming from one historical event happened in northern Taiwan, the Geelong earthquake and the tsunami in 1867. In that event, people found the tsunami deposit. So this is me, and the people found the deposit here. And this one, I don't know. And that event was very important because that event happened here. We have nuclear power plant 1, 2, 4 located nearby. And the distance from here to here is only 20 kilometers. And if you put 20 kilometers to this place is Taipei City. So it's very dangerous. And this event was written by so many different languages, including Chinese, Japanese, and the Dutch, and English, and the French, a lot of different languages. They said the tsunami actually up to the tsunami high was 6 to 7 meters. And recently we found some evidence, not us, my friend, that he said the tsunami high reached to 12 meters. So that 12 meters actually, if that one is true, then the nuclear power plant has to be shut down by law. Okay. So in this event, people found the tsunami wave height around this area was 6 to 7 meters, and they saw smokes because of volcano. And the sea bed exposed in this area. Okay. 100 dead. Very strangely, we tried to rebuild this event, but failed. They, from the earthquake scientists, they say the event will be around magnitude 7 to 7.1. I use magnitude up to 8. The wave height only have 3 meters. No matter how, I can only reach to 3 meters. So that means there have some other different mechanism that cause the event. Very possible because they have Okinawa trough. So you can see the slope here is very steep. So my Okinawa trough, Ryukyu change. Yeah. And so we think it might cause because of the landslide tsunami. So underwater landslide makes tsunami. And also that we have undersea volcano. If we study this one, then no matter how I always cannot say I know this event is caused by the earthquake or landslide depth is 12 or 13 kilometers, and the slope is 10 to 11. There are a lot of parameters make the answer cannot converge. So I'm thinking, the traditional way to study this case is that we create another and I always cannot say the number is enough. So I want to develop a method that can help us analyze the potential tsunami systematically. So instead of simulating all the possible scenarios, I want to check back from this location, from the study location, to see which area is going to affect us. So this is important because if you just check the tsunami the threat from the distance, you might be confused, just like the Japanese case. I give people this case. Here is Taiwan, northern Taiwan, Keelung. And here distance is about 100 to 100 kilometers, which is very close to Taiwan. And here is also maybe 80 kilometers. Two events are very close to each other. One, the energy propagate to the northern direction. The other case, the wave just attacked Keelung. So these two cases are, the sources are so close, but the results are totally different. So that give me the idea to show you this new method called impact intensity analysis, IIA. So in this method, it's very straightforward. We have a study area. Then we calculate each unit source case by case, just like solve the Green's function for the tsunami. And I record all the largest wave height for each case. And this one at the end will give me this map. So this map shows that if a tsunami happened here, then most of the energy will not transfer to Taiwan, almost 0%. But if that happened here, then almost 100% and tsunami energy will arrive to this area. So, and also you can see here, we have another hot zone. And here, we have some location up to this is dangerous to Keelung. That means at least I can very fast ignore the blue area, because those area, even tsunami happen, that won't affect my study area. So like screen out a lot of impossible areas. So this shows that previously A case is here, the energy goes up. B case will transfer to this area. So if we want to monitor the possible dangerous earthquake for nuclear power plants or for some buildings, then we know the priority. The highest priority we have to be careful. The lowest priority maybe can be wait. So here shows some results for the YAP. Taiwan is here, YAP is here. Do you remember the YAP will affect Taiwan? Here you can see very clear the energy pass up to this point. So the energy tsunami case scenario will transfer to Taiwan. Also, the other case is this area. This area is colored in very light color, and the energy will go to Japan. So this helps us to understand that in this event, in Keelung event, actually the most possible wave tsunami is caused underwater landslide, and this results accidentally same as the result for my colleague. He used a boat to do the measurement. They have same result as mine. Okay, so very good. So then from this one, I also think maybe I can do something more, because that means if this one colored in blue, that means you need a very strong earthquake to generate enough energy to affect Keelung. And here that means small earthquake, even a very tiny small earthquake can affect Keelung. So then we convert this map into STR. Because people probably won't understand IIA, but they might understand this map. So now I'm going to show you how to read this one. STR shows for this map, okay? And the study area is here. Here. Based on the Central Weather Bureau, they say they have different warning level for tsunami. 1 meter, 3 meter, 6 meter, so on and so forth. Here shows 1 meter result. That means earthquake in this area has to only reach to 7.5. Then in Tainan, the study area in Tainan will have 1 meter wave height. But if the earthquake happened here, then the earthquake has to be 9.5 to create 1 meter wave height in Tainan, because this side is on the lee side of Tainan. The other one is 3 meter. That means here you have to reach about 7.8 to reach 3 meter wave height. And here is very huge. And 6 meters, here you need to have maybe magnitude 8. So as you can see, here's a change that's notorious Manila change. So for the village, the chief of the village, they only need this map. When they know the earthquake location and the magnitude, check this 3 map, they know what will the wave height be in their village. So that's why I say we don't need electronic device. Only 3 map will solve the case. I think that would be very helpful for different area. So finally, as I said, I have the early warning system, but the parameters might not be accurate because the magnitude 8.0, it might be this kind of shaking or this kind of shaking. This kind of shaking will cause earth tsunami, but this kind of shaking will not. So how can we identify the shaking type? And then I'm thinking maybe I can use ionosphere. When the huge earthquake or tsunami came, the ionosphere will be interfered. So I just need to watch the interference or disturbance for this is the Earth, this is ionosphere. I only need to watch the surface, then I can know if the earthquake or tsunami really happened. How to do that? We don't need a satellite. We just need GPS. So it's totally free. I believe everybody use car navigation for GPS. So GPS, you can know the distance from GPS to your car, from GPS to your car. So basically 3 GPS, 3 satellites, you can know the location of your car. 4, you can do the calibration, and many better. Okay, but the signal from the satellite to your car has to penetrate the ionosphere. If the ionosphere is calm, then your GPS will be very accurate. If the ionosphere is disturbing, have wavy surface, then your car locations will drifting. Will have a very big mistake. So for car navigation, we try to ignore those disturbance. But other people's trash is our treasure. In the tsunami hazard mitigation, we ignore the regular signal, keep the disturbance. So when the tsunami came, the ionosphere was perturbed by tsunami, and we call this one ionami. So this is the result for 2011 Tohoku earthquake. You can see that this is the result from ComCom. This is the result from the ionami. You can see that when the earthquake happened, you can see a very fast wave coming out. It's a shock wave, but it will disappear very fast. Then followed by the tsunami wave, the one and the tsunami wave. Mr. Tsai is working on this one. He tried to create a map, a model that can calculate the disturbance from ocean surface to the ionosphere surface. But for current stage, we only need to identify if our parameter is correct. So when we see this one, then we know if the tsunami really generated or not. After that, we can follow by the parameters we create from our model. And that will largely reduce the false alarm. So here shows some detailed results, the detailed comparison. Okay. So very, very good comparison. So reach to my conclusion, sorry, takes a long time. Thank you, Dr. Simon Lin, because without his help, we cannot reach to this stage. And inundation and run-up are very important for the hazard mitigation. But inundation and the run-up depends on the good bathymetry data, because that's the key to the good inundation results. And we are trying to produce a low-cost, robust tsunami early warning system. And our NAMI from GPS can help us to identify the tsunami. IA and STR can be very useful, as I said. And at the end, we want to contribute to the Society for Tsunami Hazard Mitigation. Okay, so this is my talk, and thank you very much. There's no time for questions.
I know. I just want to confirm the impact intensity analysis is still a forward simulation. It's only you only take into account the grouping functions. Yeah. Okay. So you just basically you don't want to see the unit and the unit source. You don't see the effect on the wave. That's it. So you still have to. I mean, you know,
right.
It's not inversion method. No.
I can do the inversion. No, actually, very, very simple.
Yeah.
But inversion cannot do the inundation based on this method. Yeah. So I don't want to use this to do the inversion, because we have the very fast calculation finish in 1 minute. I don't need that.
It's the. Right. I mean, it's the Keelung tsunami well understood. I mean, it could be 12 meters, and then the previous only show 1 meter. So do you think that issue is fully understood, the Keelung?
I cannot say fully, but much better than before.
Okay.
Yes.
Okay. And then about the tsunami and the seismic relationship, you basically using the the previous result, and try to see the relationship, right? That's okay. Yeah.
No. We have built a lot of.
You're running different scales of.
No. Because this is a linear system. Okay. So we do a 1 meter simulation. We can extend to 0.5, 0.3, 1.2 something. Yeah. The key is that there's a very complex calculation from IAA to STR. Mm-hmm. So we have to transfer those information back to magnitude. Okay. So that's the difficulty. Yeah.
And the ionosphere information, I think, that's very clever actually, but it's because people try to use the ionosphere information, try to predict the earthquake, the happening earthquake. But what you're doing is actually very clever. You only use the informations of where you call the noise, right? But then I don't know about I mean, it's obvious that we can do that if earthquake nearby, but if earthquake, I don't know, it actually will have big disturbance on the sea surface. We think that's very significant. So the GPS emission can be caught, but then you don't have anything there, right? On the side, near the side.
We don't need the because we need GPS. We don't need GPS very on that side. Just close to the side will be enough.
Yeah.
Yes.
So, but I know if it's say like and there was no GPS information you had over there.
Yeah, then we need to put some. It's relatively cheap actually.
Put to the GPS
GPS station. Yes.
Yeah. But then tsunami buoy is still quite expensive.
Right.
Several millions.
Yeah.
For a few there. Okay. Yeah. Thank you. But this is very clever. Yeah.
Okay. So we still have one more speaker. It's Dr. Eric Yen. He will be giving a talk on disaster mitigation collaboration in Asia, current status.
Dr. Eric?
Yes.
You send us your presentation. We can stream it from our side on YouTube.
For the sessions in the afternoon, right?
Or now as well. Otherwise, now on YouTube, it's only your camera that is shown.
Yeah. Okay. Yeah. We can do the adjustment in the.
Okay. Okay then.
Okay. Let's finish my presentation in 10 minutes, and then we do the adjustment after lunch. So my presentation is about the current regional collaboration on disaster mitigation. But firstly, I have to explain the DMCC, as mentioned in the previous speakers. That's the Disaster Mitigation Competence Center. That's one of the 8 competence centers in the EGI Engage project. Yeah. The EGI Engage project started from March 2015 and ended in this month, and with partners from Taiwan, Philippines, Malaysia, Indonesia, and Germany. In the beginning, we have Thailand as a partner, but turns out Thailand cannot join us in the end. So the goal is to improve the strategy of prevention and reduction of disaster. Simply speaking, in the DMCC collaboration, we've been build up the collaboration among the scientific group, the user community, the infrastructure, and also the application support community. So we've been finished several case studies as presented by Professor Wu on the tsunami, and also others, which will be mentioned later. So in this project, which is going to end in this week, tomorrow. So the DMCC produced 3 deliverables as listed here. So we generated 2 simulation portals. The first one is the wave portal for the weather simulation. The second one is the wave portal for the tsunami wave propagation, which will be demonstrated in the afternoon at 5 o'clock to 6 o'clock by Dr. Tsai. So based on the works from the DMCC leading by Professor Simon Ling, actually our collaboration with the European e-science projects could be dated from 10 years ago. So we've been working based on the e-infrastructure on the disaster mitigation has been several years. So DMCC is the latest one. So it's very naturally that we combine the collaboration efforts of the DMCC and also the APEN. So in APEN last year, we initiated the disaster mitigation working group here because we can reach out to almost every Asia countries. So in this working group, we like to sharing the knowledge and experiences and resources from the case study from DMCC. Yeah. So we hosting disaster mitigation working group like today in almost every APEN meeting in the past 2 years, and we'll keep going on. So it's very useful to have such a collaboration between the GMCC and also the APEN disaster mitigation working group. As I mentioned in my previous slide, actually the working group also likes to working with other APEN working groups such as agriculture and also the cloud computing working groups together. So we can engage more local user communities from different countries and also resources from different Asia countries together. Again, the approach of deep understanding has been proved to be very, very essential and useful for the disaster mitigation. And here's the that's the common interest in terms of the disasters in Asia countries. Besides, the graph also showing the connections, because most of the time the hazard comes not just one by one. Some of them are relationships between the multi-hazards. So that scenarios has to be taken into account. And in the lower half of this graph, so based on the study and research from the scientific group like Professor Wu, they provide us the innovative simulation models. So we use this model to the studies, and then from the case study we can improve the theory, and so that's the cycles of the approach. So in the past 2 years in the DMCC, we've been working together with Philippines on the types mentioned by Professor Wu, and also working with the Malaysia on the Malaysia flood has been demonstrated by Professor Lin, and also we have the simulation result from Thailand on the Thailand flood case, and we are currently working with Basuki in Indonesia on the long distance dust transportation from the forest fires. So last year or 2 years ago in the APEN meeting disaster mitigation working group, we have the participant from Nepal, so they are also bring their case study to this working group, and then we can work together. So this is the another models of these collaborations. So in the right hand side, for the past 2 to 5 years, we've been developing the tsunami simulation, weather simulation, and storm surge simulation models. So they are accessible through the web interface. That means the user could make use of the simulations just using your browsers. And then we are collecting all the materials from the case studies and keep on sharing those results and also knowledges, everything, data from the case studies to support the future cases, to support the other case studies in different countries. And then we are closely integrated with the regional infrastructures to support the federations of the resources from different places. And we, as I mentioned, we've been build up the collaboration framework from the scientists, from the end users, from the application developer, from the IT support, and also from the infrastructures. And here's the integration of the atmospheric model and also the oceanic models from the Philippine Typhoon Haiyan case studies. So because of the time, I think I should skip those. And in the DMCC collaboration, actually the partners of Germany, they provide the advanced visualization facilities for these collaborations. So you can have a new ways of a visualization of the disasters details. And here are the user interfaces of the ICOM CART systems, and also the WAF. And the storm surge systems will be demonstrated in the afternoon. So in the future, the multi-hazard risk analysis, including the geophysical characteristics and the triggers, and also the combination of among different hazards will be taken into account. But that's up to the case study. So we like to have every partners in Asia partners. We welcome you could bring your resources, your case study, your users together. The collaboration is always open. Yeah. Several lessons learned from the past few years from the DMCC case studies, here were listed for your reference. And so, based on the deep understanding and the regional infrastructures, so we providing the simulation portals. We keep working on different case studies in different countries, and we hope to provide the services of the knowledge base to share. So maybe we don't have time to talk about this. That's the as I mentioned, the DMCC, the EGI Engage project will end tomorrow. The next phase will be the EOAC projects funded by European Commission. That means what we call that, Open Science Cloud. And we with DMCC is we have another phase of the disaster mitigation competence center in the new phase of the European funded e-science project called Open Science Cloud. Started from next year, the January 2018, for 3 years. So the DMCC will keep on building up the capacity on the disaster mitigation based on the numerical simulations, facilitate the sharing of all kinds of resources and extending the collaboration, especially working together with the APAN. And in the future, we also like to work with APAN to have funded support from the Asia Connect. So MCC, maybe we can have a detailed discussion in the afternoon or in tomorrow. So the partners of the DMCC, we have 8 partners from 8 Asia countries, and also 4 European countries together. So in this collaboration, we like to have a case study in almost every partner countries. So this table is still open. So because the project now is granted, so we have time to finalize the case study from each countries and the contributions from different countries. So some of the details of the tasks and the deliverables of the DMCC. So that's the